Hello everyone, and welcome to today's presentation. I'm excited to have you here as we explore the activated sludge process control and troubleshooting. This presentation is based on a methodology developed by the Ohio EPA Compliance Assistance Unit, drawing on lessons learned from experienced operators. We'll be discussing a streamlined approach to diagnosing problems in the activated sludge process and simple methods for daily process control. Over the next few slides, we'll cover how these techniques evolved from years of fieldwork, helping facilities quickly identify issues and maintain NPDES permit compliance with minimal effort. I look forward to sharing this valuable information with you. Let's take a closer look at the foundation of the process: ammonia conversion. Why does ammonia matter in wastewater treatment? Well, wastewater contains pollutants like carbon in the form of CBOD and ammonia nitrogen, or NH3. The bacteria in the aeration tank play a crucial role here. They convert these pollutants into new bacterial cells, which is biomass, and into more desirable substances like carbon dioxide and nitrate. This conversion is vital because it helps prevent the degradation of the receiving stream, protecting our environment. Now, it's important to understand that nitrifying bacteria are very sensitive to environmental conditions. Monitoring how well ammonia is converting into nitrate gives us an early warning system, kind of like a health check, so we know when process adjustments are needed. If something limits these bacteria's effectiveness, we'll see an increase in ammonia levels in the aeration tank effluent, signaling that we've lost some control over the process. Here's a critical point. If the clarifier effluent ammonia is less than 1 mg per liter, that means we've successfully converted most of the pollutants, both CBOD and ammonia. At this stage, the aeration process is essentially complete. But if ammonia levels exceed 1 mg per liter, that indicates incomplete conversion or possibly that ammonia is being generated downstream in the clarifier. Now, let's talk about what the nitrifying bacteria need to do their job effectively. They require adequate dissolved oxygen, more than 2 mg per liter, and sufficient alkalinity, over 100 mg per liter. Temperature is also key. Above 10 degrees C is ideal for bacterial activity. And of course, they need the right bacterial population to carry out the process efficiently. Remember, ammonia is only converted to nitrate in the aerobic, or oxygen-rich, environment of the aeration tank. It's important to note that this process doesn't happen in the clarifier. Ammonia can pass through to tertiary treatment if it's not fully converted. So, understanding and maintaining these conditions ensures our treatment process stays effective and environmentally safe. Let's talk about how we locate the problem when it comes to high ammonia levels, specifically comparing the aeration tank and the clarifier. When we see that the ammonia in the clarifier effluent exceeds 1 milligram per liter, the first step is to pinpoint where the issue is actually originating. The initial diagnostic step is to measure the ammonia in the aeration tank effluent. This helps us determine whether the problem is happening upstream or downstream. Now, if the ammonia in the aeration tank effluent is greater than 1 milligram per liter, that indicates the source of incomplete conversion is inside the aeration tank itself. In this case, we need to gather data from that tank. Look at factors like temperature, dissolved oxygen, alkalinity, biomass concentration, and loading conditions to identify what might be causing the inefficiency. On the other hand, if the ammonia in the aeration tank effluent is less than 1 milligram per liter, but the clarifier effluent shows high ammonia levels, then the problem lies in the clarifier. Here, all the ammonia was initially converted in the aeration tank, but it's being regenerated or broken down in the clarifier through bacterial lysis. The key takeaway is this: always identify where the high ammonia is first. Once you know the location, you can direct your operational adjustments precisely to that unit. Trying to troubleshoot or make adjustments to the wrong part of the process, say, adjusting the clarifier when the issue is actually in the aeration tank, is a common mistake and can lead to ineffective solutions. So remember, pinpoint the source first, then focus your efforts there. That's the most effective way to troubleshoot and resolve high ammonia issues efficiently. Let's talk about water temperature, which is a crucial environmental factor affecting nitrification. The temperature of the water in the aeration tank directly influences how fast the nitrifying bacteria grow and perform their job. These bacteria are responsible for converting ammonia into nitrate, a key step in the treatment process. When temperatures in the aeration tank fall below 10 degrees Celsius, these bacteria may not reproduce quickly enough to keep up with the ammonia load. This can lead to incomplete ammonia conversion, which impacts overall treatment efficiency. Now, as bacteria work to convert waste, they generate heat, which helps keep the water temperature above that 10-degree threshold. Typically, the process maintains temperatures above 10 degrees Celsius, but there are exceptions. For instance, low-influent organic loading produces less heat, and overaeration can expose the tank to colder ambient air, leading to heat loss. This brings us to the main problem. Overaeration in low organic load systems can cause water temperatures to drop below 10 degrees, inhibiting nitrification and wasting electricity in the process. So, how do we measure and correct this? The key is to measure the water temperature in the aeration tank effluent using a dissolved oxygen meter. If you find the temperature below 10 degrees Celsius and the dissolved oxygen is above 2 mg per liter, it's a sign that aeration is causing heat loss, and adjustments are needed. To prevent this heat loss, there are several solutions. First, reducing aeration capacity by removing tanks from service during low-load seasons, like in campgrounds or schools on break, can help. Adjusting the timers to reduce aeration cycles also minimizes cold air exposure while still maintaining enough dissolved oxygen. Additionally, insulating the tanks with covers or tarps can prevent heat transfer to the atmosphere. For upstream areas like flow equalization basins, covering them during extreme cold can also protect against heat loss. One thing to keep in mind is that the return systems, like the RAS, are controlled by aeration on cycles. So, when you're adjusting timers, you need to consider how these systems interact to avoid unintended consequences. In summary, managing water temperature is vital for effective nitrification, especially in colder conditions, and small operational adjustments can make a big difference in maintaining treatment efficiency. Let's take a closer look at some clarifier problems related to ammonia re-release and what causes bacteria to go bad in this process. First, bacterial cells are built from carbon and nitrogen. When aerobic bacteria end up in an oxygen-free environment for too long, they die and break apart, a process known as lysis. During this breakdown, bacteria release ammonia nitrogen back into the water. Now, if we see that the ammonia levels in the clarifier effluent are higher than in the aeration tank, that's a red flag. It indicates bacteria are breaking down in the clarifier rather than in the aeration tank, causing ammonia to be released where it shouldn't be. Next, let's talk about scum baffle accumulation. Biological foam forms in the aeration tank and can migrate to the clarifier, building up behind the scum baffle. Over time, this foam lyses and releases ammonia nitrogen into the water. Since clarifiers don't remove ammonia themselves, this ammonia passes straight through to the effluent. The key here is maintenance. Regularly cleaning the scum baffle area helps prevent foam buildup and bacterial breakdown, reducing ammonia release. Moving on, excess biological foam on the clarifier surface is another issue. When there's too much foam, it can overload the scum baffle and spread across the entire surface. Brown foam, in particular, shows that there's more biomass than the system needs. This low FM ratio indicates overgrowth. The solution is to control foam formation upstream in the aeration tank. We can do this by adjusting the FM ratio, either increasing wasting or reducing aeration to cut down on foam generation. Finally, sludge blanket depth plays a role too. As the sludge blanket gets deeper, bacteria are more prone to lyse and release ammonia. If you see a dark or black layer in the sludge blanket, that's a sign of potential ammonia release happening. To manage this, We should regularly monitor the sludge blanket depth. Using a core sampler is a good method. If it gets too deep, say, over 30% of the clarifier's water depth, we can increase the return activated sludge rate or waste more sludge to keep it in check. All these points tie into the bigger picture of maintaining a healthy, stable biological process and preventing ammonia re-release that can compromise water quality. Now, let's turn our attention to the second key environmental factor, alkalinity, and how it relates to the pH buffer system. As nitrifying bacteria convert ammonia, or NH3, into nitrate, NO3, they produce acids in the process. If these acids accumulate, the pH in the aeration tank can drop, which can eventually inhibit the bacteria's ability to convert ammonia effectively. Here's where alkalinity comes into play. It's naturally present in water and acts as a buffer, neutralizing those acids and helping maintain a stable pH. When alkalinity levels are sufficient, the pH stays within the optimal range for nitrifying bacteria, allowing the conversion process to complete smoothly. But if the influent has a high ammonia concentration, or if natural alkalinity is low, the pH can drop too much, and this inhibits the conversion altogether. It's important to understand the stoichiometry here. Nitrifying bacteria need about 7.14 milligrams per liter of alkalinity for every 1 milligram per liter of ammonia they convert. Monitoring alkalinity is crucial. We measure total alkalinity in the aeration tank effluent using a field titration kit. If the alkalinity is above 100 mg/L, we can assume that alkalinity isn't limiting the process. If it's below 100 mg/L, then alkalinity is likely the limiting factor affecting nitrification. Here's a critical point. Don't just measure alkalinity once a day at the same time. You need to measure it at different times and on different days to get an accurate picture of the trends. Why is this important? Because monitoring pH alone isn't enough. pH can drop quickly when alkalinity is depleted, leading to sudden process upset. So, our goal is to provide enough alkalinity to prevent that pH drop in the first place. Monitoring alkalinity gives us early warning signs, whereas pH tells us when it's already too late. If alkalinity drops below 100 mg/L, it's time to supplement, often with sodium bicarbonate. And for higher ammonia loads, or very low natural alkalinity, we might need stronger alkalinity sources. In summary, maintaining proper alkalinity is vital for stable nitrification and overall process health. Let's talk about environmental factor number 3, dissolved oxygen, or DO, and why it's so critical. The oxygen requirement is essential because nitrifying bacteria in the aeration tank need a sufficient supply of dissolved oxygen to do their job effectively. If there's not enough DO available, the bacteria can't convert ammonia properly, which can lead to the effluent ammonia levels exceeding 1 milligram per liter. That's why field monitoring of DO levels throughout the aeration tank is so important, to identify if oxygen deficiency is causing incomplete conversion. When it comes to measuring DO, we need to consider that concentration depends heavily on the load in the tank. So, to get an accurate picture, we should monitor at different times of the day and on different days of the week. This helps us identify both peak and low points in DO levels. Using a data logging DO meter can be very helpful here, as it allows us to track trends over extended periods and make informed operational decisions. Now, where should we measure DO? Ideally, at multiple depths and locations within the tank to get the best overall picture. But the most critical spot to focus on is the effluent, because that's typically where you'll see the highest DO levels, and it gives us the clearest indicator of overall performance. As for the target DO concentration, aiming for around 2 milligrams per liter in the effluent is usually sufficient for complete conversion. However, if we find that overaeration is lowering the water temperature, we might need to reduce the aeration run time to optimize conditions. And if DO levels are low, there are several ways to improve the situation. We can increase blower runtimes, open partially closed valves on the diffuser pipes, clean the diffusers to ensure proper oxygen transfer, or even bring additional aeration tanks online if necessary to boost capacity. All of these strategies help ensure that the nitrifying bacteria have the oxygen they need to do their job efficiently, which ultimately supports the overall process performance. Let's talk about biomass management, or what I like to call the balancing act. The key idea here is understanding the biomass requirement in the system. The CBOD and ammonia nitrogen entering the aeration tank act as food for the bacteria, or biomass. These bacteria need to consume or convert all the waste into new bacteria or harmless byproducts before they leave the tank. When influent loadings increase, it's crucial that we have enough biomass to ensure complete ammonia conversion to nitrate. Estimating how much biomass we have can be done quickly using a centrifuge, usually in about 15 minutes. It's quite accurate for process control purposes. What's more important than knowing the exact amount is understanding the relative concentration and whether it's trending up or down over time. Now there's a real sweet spot here. As biomass concentration increases, the tank can theoretically handle a higher organic load. But there's a limit. When biomass exceeds about 4% by centrifuge, proper settling can slow down or even get inhibited, which causes sludge blankets in the clarifier to rise and can lead to operational issues. So how do we measure and adjust? The centrifuge is our go-to tool for quickly identifying biomass levels. Typically, concentrations are between 2% and 4%. Watching the trend over time is especially useful for making control decisions. If we see ammonia levels greater than 1 mg/L and the centrifuge indicates low biomass, that's a sign we should increase biomass concentration. We can do this by decreasing the sludge wasting rate. Then, we should monitor the ammonia in the effluent. If our process is working, ammonia levels should drop as biomass increases. It's all about finding that balance. Increasing bacteria helps with conversion, but too many bacteria, especially above 4%, can slow settling rates in the clarifier. To be sure solids aren't hiding in the wrong place, it's good practice to do core sampling in the clarifier. And if our RAS pump isn't working properly, solids might be collecting in the clarifier rather than the aeration tank, which can skew our readings. So, managing biomass is really about maintaining that optimal level, enough to handle the waste, but not so much that it hampers settling and overall process efficiency. Let's take a closer look at the loading rate analysis. The key question here is your system overloaded? To figure that out, we need to determine if the influent organic loading exceeds what the system was designed to handle. This involves collecting the average influent flow and average influent BOD data. Once we have those numbers, we can calculate the actual loading. The formula is straightforward. Multiply the influent flow in million gallons per day, or MGD, by the influent BOD in milligrams per liter, then multiply the result by 8.34. This gives us the pounds of BOD per day. For example, if we have an influent flow of 0.015 mgd and an influent BOD of 200 mg/L, the calculation looks like this. 0.015 times 200 times 8.34, which equals approximately 25 pounds BOD per day. Next, we need to determine the aeration capacity of the tank. To do this, we calculate the volume in cubic feet by multiplying the length, width, and water depth of the tank. Say our tank is 12 feet long, 6 feet wide, and 9 feet deep. That's 12 times 6 times 9, which equals 648 cubic feet. To convert that to thousands of cubic feet, we divide by 1,000, giving us 0.648. Now, to find the organic loading rate, we divide the actual loading, our calculated pounds of BOD per day, by the aeration capacity in thousands of cubic feet. Using our example, 25 pounds divided by 0.648 equals about 38 pounds per day per 1,000 cubic feet. It's important to compare this value to the design standards. Typically, for extended aeration systems, the design range is between 15 and 25 pounds BOD per day per 1,000 cubic feet. If your actual loading exceeds this range, it suggests your system might be overloaded, and conversion might be incomplete. So, what do we do if the actual loading is higher than the design? Well, we need to evaluate potential modifications to improve treatment efficiency. Options include better flow splitting, increasing flow equalization capacity, implementing pretreatment to reduce high-strength loads, switching from coarse to fine bubble diffusers, or even adding additional aeration tanks. Overall, understanding and managing loading rates is crucial for maintaining effective treatment and ensuring your system operates within its design parameters. Let's take a closer look at the settling characteristics through the settleometer test. This test helps us evaluate how well the biomass is settling out of the treated water, which is crucial for overall process performance. One of the key indicators is the ammonia level in the effluent from the aeration tank. If it's less than 1 milligram per liter, that tells us we've successfully converted all the organic waste into bacterial cells. Essentially, the aeration tank has done its job properly. Now, the next step focuses on separating these bacteria from the clean water in the clarifier. This separation depends on the biomass's settling rate, which needs to be maintained at a proper concentration to allow gravity to do its work effectively. A common target we aim for is that within 5 minutes, the settled biological mass should be below 80%. Achieving this indicates the clarifier is performing adequately and that the biomass is settling well enough for efficient operation. Why 5 minutes? Because the first 5 minutes of the settleometer test most accurately reflect the true settling characteristics. Beyond this window, concentration effects can start to skew the results, so this period is our most reliable measure. Think of the settleometer as a perfect clarifier. It's a controlled environment with no hydraulic currents from influent or return flow that might disturb settling. This ideal scenario helps us understand the maximum potential of settling rates. If the biomass settles too slowly and can't reach below 80% within 5 minutes, it's considered slow settling or inhibited. Such slow settling biomass can be easily carried over the clarifier weir, potentially impacting water quality. It's important to note that settling rates below 80% in 5 minutes shouldn't cause solids loss. But if we want to be more conservative, we could lower that threshold, for example, to 70%, to tighten control. Finally, both goals are essential. First, maintaining the effluent ammonia below 1 milligram per liter, and second, ensuring the biomass settles at an adequate rate. Both are necessary to achieve compliance and ensure our process runs smoothly. Let's talk about diagnosing slow settling in the clarifier, specifically focusing on concentration versus density. When we observe that biomass doesn't settle below 80% within 5 minutes, that's a clear sign there's a problem with the settling characteristics. This can lead to biomass loss from the clarifier, which we definitely want to avoid. The first step is figuring out the cause. Is it that the biomass concentration is too high, or is it that the biomass density is too low? To do that, we can use a simple diagnostic test involving a centrifuge. By spinning a sample from the aeration tank, if the concentration exceeds 4%, slow settling is usually due to high biomass concentration. This helps us pinpoint whether excessive solids are the issue. Another useful tool is the 2-minute diluted settleometer test. This test compares how quickly the undiluted effluent settles versus a sample that's been diluted 50%. It provides insight into whether the problem stems from concentration or density. Now, interpreting the results is crucial. If the diluted sample settles significantly faster than the undiluted one after 2 minutes, that indicates a concentration problem. In this case, increasing wasting to reduce the biomass concentration should improve settling. On the other hand, if the diluted and undiluted samples settle at similar rates, then we're likely dealing with a density issue. Here, the biomass is lightweight, often due to filamentous types, which affects how it settles. Finally, some visual clues can help us confirm these findings. Dense biomass may settle so quickly that it doesn't filter suspended solids effectively, leading to a cloudy supernatant that gradually clears. Filamentous biomass, however, often shows a conning effect, a depression forming in the center of the settleometer after about 30 to 60 minutes. Recognizing these signs helps us tailor our approach to improve settling performance. Let's take a closer look at the issue of filamentous bacteria and the low FM problem. When we talk about identifying this condition, one key indicator is the 5-minute settleometer result. If it's greater than 80%, that suggests the settling rate is too slow, which points to filamentous bacteria overgrowth. Similarly, if the aeration tank concentration is below 4%, or if the 2-minute diluted settleometer shows slow settling, these are strong signs that excessive filamentous bacteria are present in the tank. Another visual clue to watch for is the brown foam indicator. Excessive brown foam on the aeration tank or the clarifier surface indicates biological foam growing in a low FM environment, especially when the MLSS levels are high. This foam can migrate across the system and eventually cover the entire clarifier surface, disrupting normal operations. Now, a very clear supernatant during the settleometer test is also a red flag. When the supernatant appears crystal clear, it's often because filamentous bacteria are acting like a filter. They trap small flocs and debris, which then get incorporated into larger, problematic flocs. You might also notice the conning effect. After about 30 to 60 minutes, a depression or cone can develop in the center of the settleometer. This happens because the biomass density drops due to the overgrowth of filamentous bacteria, creating that characteristic cone shape. So what's the solution? Primarily, we need to increase the wasting rate. In domestic activated sludge systems, operating within a 2% concentration range is typical. When concentrations exceed 4%, settling slows down because of the high biomass levels. By gradually increasing the sludge wasting rate, we can reduce the biomass in the aeration tank. It's important to do this slowly, monitoring the effects. If we waste too much too quickly, it can lead to increased ammonia in the effluent, signaling that we've gone too far and that the biomass reduction is impacting treatment efficiency. In essence, controlling filamentous bacteria involves a careful balance, adjusting the wasting rate to restore proper settling without compromising overall treatment performance. Let's talk about filamentous bacteria and the low dew problem. One common environment in aeration tanks that promotes filamentous growth is when the oxygen levels are low. Now, it's important to differentiate this from low FM conditions, which usually produce brown foam. In low dew situations, you typically won't see heavy brown foam. A key indicator that you're dealing with low dew rather than low FM is if the effluent from the aeration tank has ammonia levels significantly above 1 mg/L. In contrast, low FM conditions usually keep ammonia very low, below 0.3 mg/L. To properly identify low dew issues, I recommend using a data logging dew meter. This helps you evaluate how long and how often the dew levels drop below 1 mg/L. Remember, you don't always need to keep dew above 2 mg/L, but the longer and lower the dew stays, the more likely filamentous growth will occur due to low oxygen conditions. So, what's the solution? If low dew is causing filamentous bacteria, you need to adjust your aeration system to better match the influent organic loading. This might include increasing aeration cycle durations during low dew periods or bringing additional blowers online when needed. Also, it's worth evaluating your aeration distribution system. Check for clogged diffusers, pipes, or valves that could impair oxygen transfer. Additionally, assess the mixing intensity of your aeration pattern, since poor mixing can exacerbate low dew conditions. Finally, a visual cue to consider. Healthy aerobic biomass usually appears light to dark brown depending on concentration. If the biomass looks more gray, that's often a sign that dew and mixing are limited, which can lead to filamentous growth issues. By monitoring these factors and making targeted adjustments, you can better control filamentous bacteria growth and maintain a healthy aerobic environment in your tanks. On this slide, we're looking at filamentous bacteria and their septic sources, which is the third key environmental condition to consider. Typically, we see filament growth in conditions where the food-to-microorganism ratio, or FM, is low, and dissolved oxygen levels are also low. But there's an additional factor we need to watch for, specifically, influent loading or internal side streams that contain byproducts of septicity, like organic acids and hydrogen sulfide. Now, let's talk about collection system sources. Septic influent can come from various parts of the collection system, especially those with long force mains or low flow conditions. These scenarios promote solids deposition within the pipes. Industrial dischargers are also a common source. If you notice a strong, rotten egg odor in the influent, that's a clear sign of septicity in the collection system. That hydrogen sulfide odor indicates that septic conditions are present, and that products of septicity may be promoting filament growth. Moving on to the headworks condition, hydrogen sulfide is generated when septic conditions develop in the collection system. If you see significant corrosion here, it might be a sign that septicity products are contributing to filamentous bacteria growth in the aeration tank. Lift stations can also exhibit corrosion signs, which again points to septic conditions upstream. Next, let's consider influent characteristics. Usually, domestic wastewater appears gray in color. But if you notice the influent is darker, more blackish, that suggests it might be coming from more anaerobic or septic sources. Sometimes, just a visual inspection can help identify potential septicity, even if you don't detect any odors. Finally, internal side streams are important to monitor. For example, aerobic digesters that have been left unaerated for a while can generate high ammonia concentrations. When that sludge is decanted back into the treatment system, it can look like nitrification is being inhibited. So, it's crucial to check inside the fence first. An internal recycle with a high ammonia load can be a self-inflicted wound, contributing to filamentous bacteria issues. So overall, recognizing these signs and understanding their sources helps us manage filamentous bacteria growth more effectively and maintain a healthy treatment process. Let's talk about clarifier hydraulics and how they prevent solids loss, especially when the biology looks good but solids still escape. When biomass settles properly, say, below 80% in 5 minutes, that usually indicates the settling characteristics aren't the issue. But solids can still be lost because of hydraulic problems. There are 3 common design features that can cause this. First is uneven flow splitting into the clarifiers. If the flow isn't evenly distributed, some areas might be overloaded, leading to solids escaping. Second, density currents within the clarifier can carry solids over the weir. These occur when denser sludge flows between layers. And third, the position and height of weirs play a significant role. If they're not properly located or elevated, solids might be carried out with the effluent. Now let's look at the sludge blanket depth. As biomass settles, a dense layer or blanket forms at the bottom. The deeper this blanket gets, the less capacity the clarifier has. Plus, if the blanket gets too close to the surface, say over 30% of the water depth, solids are more likely to be carried over the weir. To keep an eye on this, use a core sampler to measure the depth regularly and ensure it stays below that 30% threshold. Next is the RAS, or return activated sludge pumping rate. It's crucial that this rate matches the settling rate of the biomass. If the biomass settles slowly, the RAS should be slow. If it settles quickly, then faster. Relying on a fixed percentage of influent flow for RAS rates is tempting, but often incorrect because it doesn't account for actual settling conditions. Remember, the pump can only remove what has already settled at the bottom. Moving on to flow splitting. Devices that split flow horizontally often can't evenly distribute flow to downstream tanks, especially when flow rates change. The best method is to use a flow splitter box designed with upward-directed flow and equal-length weirs at the same elevation. This setup helps maintain a balanced load and prevents solids from being carried away. Finally, density currents are another factor. When mixed liquor enters a clarifier, the different densities, sludge versus supernatant, can cause flow between layers. This momentum can push solids over the weir. Installing properly placed baffles helps break up these currents, preventing solids from escaping and maintaining solids retention within the clarifier. All these hydraulic considerations are vital to ensuring our clarifiers operate effectively, and solids are retained as intended, complementing the biological processes we've optimized. Let's talk about the operating window for achieving compliance in our treatment process. Think of it as the sweet spot where everything works most effectively and efficiently. On one side, we have the ammonia levels in the clarifier effluent. If they are less than 1 milligram per liter, it means the conversion process is complete. On the other side, we look at the settleometer. If the biomass settles more than 80% within 5 minutes, separation is adequate. This area between those two process control points is what we call the operating window. Maintaining our system within this window ensures we get the best effluent quality with the least amount of effort and expense. Keep in mind, as organic and hydraulic loads change, so does this window. When we apply more pressure to the system, the window tends to shrink. But with proper measurement and adjustments, we can keep the process centered in this window, what we call the safest, most optimal position. Now let's consider the dynamics of this window. When the system is under stress, the window contracts, but when conditions are favorable, it expands. The bottom boundary is set by the settleometer, 80% or more biomass settling within 5 minutes. The top boundary is defined by ammonia levels, less than 1 milligram per liter, indicating complete conversion. The goal is to operate within this safe zone, between those two limits. Temperature also plays a role here. Warmer temperatures generally expand the operating window, making it easier to stay within optimal conditions. Colder temperatures tend to contract it, so we need to be especially vigilant in those conditions. The key is locating where your system currently sits within this window, and then adjusting your process accordingly to keep it centered. Finally, I want to emphasize prevention over correction. Without proper monitoring, your operating window shrinks, increasing violations and requiring more labor-intensive fixes. Small, proactive adjustments can prevent most upset conditions, saving you time and effort. Remember, consistent monitoring and timely adjustments are the keys to sustained compliance and optimal system performance. Let's talk about RAS rate optimization and how it relates to matching pumping to settling. The key idea here is that the return-activated sludge, or RAS, pumping rate must be aligned with the settling rate of the biomass coming from the aeration tank. If we don't match these rates properly, solids can overflow the clarifier weir, which is something we definitely want to avoid. Remember, the RAS pump can only remove biomass that has already settled to the bottom. It can't pull biomass down by increasing the pumping rate. So, increasing RAS flow won't draw biomass down. It can only remove what's already settled. Now, what happens if the RAS rate is too slow? Well, if it's slower than the settling rate, more biomass enters the clarifier than we're removing. This causes the sludge blanket to build up. Think of it as a thick layer of sludge in the clarifier. When that sludge blanket gets too thick, it reduces the clarifier's efficiency and can lead to more solids escaping with the effluent, which isn't good. On the flip side, if the RAS rate is too fast, faster than the settling rate, we run into a different problem. Excess water gets returned to the aeration tank, creating additional hydraulic pressure inside the clarifier. This increased pressure makes it harder for biomass to settle properly and form a good sludge blanket. Instead, more biomass stays suspended in the water, and this increases the risk of biomass being pushed over the clarifier weir, especially if filamentous bacteria are present and dominating. Now, to quickly evaluate whether your RAS rate is appropriate, there's a handy centrifuge method. You analyze the biomass concentrations in both the aeration tank effluent and the RAS. Typically, the biomass concentration in the aeration tank is between 2 and 4%. As the biomass settles in the clarifier, its concentration increases. The rule of thumb here is that the RAS biomass concentration should be at least 1.5 to 2 times higher than that in the aeration tank. If it's less than 1.5 times, it's a sign that your RAS rate might be set too high, and you're possibly pumping out biomass too quickly. Understanding and applying these principles allows us to maintain a balanced process where solids are properly settled and removed, enhancing overall treatment efficiency. Let's take a closer look at clarifier loading rates, starting with the surface overflow rate, or SOR. This is essentially a measurement of the overflow velocity per square foot of the clarifier surface. Think of it as how fast the water is flowing over the surface. When this velocity gets higher, it becomes tougher for the biomass to settle down to the bottom of the clarifier. Now, how do we calculate this? The design limits vary depending on the size of the plant. For small package plants, the limit is typically between 600 and 800 gallons per day per square foot. For larger clarifiers with scrapers, the limit is around 1,000 gallons per day per square foot. It's important to check if, during peak flows, a single clarifier exceeds its designed SOR. If multiple clarifiers are in service, then each should be receiving an equal flow to prevent overload. Moving on to the solids loading rate, or SLR. This measures the settling velocity of the biomass, again per square foot of the clarifier surface. When the biomass loading increases, it naturally becomes harder for the particles to settle properly. The calculation here also depends on plant size. For small plants, the limit is about 25 pounds of solids per day per square foot. For larger clarifiers with scrapers, it's around 35 pounds per day per square foot. As biomass concentration in the aeration tank increases, it slows down the settling process. To address this, you can reduce the biomass in the tank or bring another clarifier online to share the load. Understanding these rates helps us maintain effective clarification and ensures our process runs smoothly and efficiently. Now, let's talk about some practical field procedures and the essential tools that you'll need in your operator's toolkit. Success in managing the activated sludge process really hinges on your ability to master a few straightforward field tests. These tests give you immediate data, enabling you to make quick and effective operational decisions. First, ammonia testing. You can use simple field test kits, like aquarium-style kits or single-parameter colorimeters for on-site analysis. It's important to verify your results by doing split sampling with your contract laboratory. When testing samples from the aeration tank, remember to centrifuge first to separate suspended solids, then analyze the clear centrate. The advantage of field testing is that it allows you to act immediately, rather than waiting days for lab results. Next, alkalinity titration. Use simple titration kits with eyedroppers to measure total alkalinity directly on site. Count the drops of acid reagent until the color changes, then multiply by the kit's factor to get your measurement. Make sure you're measuring total alkalinity, not just phenolphthalein alkalinity, and focus on the effluent from the aeration tank. It's best to monitor at different times and on different days to identify trends. Single measurements won't give you the full picture. Moving on to dissolved oxygen monitoring. Using a data logging meter is ideal because it captures peaks and valleys over extended periods. If you don't have data logging capability, take periodic measurements of the aeration tank effluent throughout the day and week to build a dew profile. Always measure at the same reference point, usually the aeration tank effluent, to ensure your data is consistent and comparable over time. For centrifuge analysis, fill 2 tubes to the 100% mark with aeration tank effluent. Spin them for about 2 minutes to determine biomass concentration by volume percentage. You should see similar results between the 2 tubes. Typically, concentrations range from 2 to 4%. You can also use centrifuges for sampling return-activated sludge or for assessing solids in the clarifier to understand solids distribution and pumping rates. The settleometer test is another quick way to assess settling characteristics. Fill the device to the 100% mark with effluent, stir gently, then hold the paddle still briefly before starting your timer. Record the settled sludge volume at 5 minutes. Aim for less than 80%. Continue measuring every 5 minutes up to 30 or 60 minutes. Watch out for the conning effect, which indicates filamentous bacteria, and note the clarity of the supernatant. Remember, this test mimics the clarifier's settling process under ideal conditions. Finally, core sampling. Lower the core sampler slowly and vertically into the middle of the clarifier hopper, avoiding spear fishing or dropping it in. You'll see 3 zones: the clear supernatant at the top, an interface zone with unconsolidated solids in the middle, and the blanket zone at the bottom with more compacted solids. Your target is to keep the blanket less than 30% of the water depth. Be aware that dark or black layers can indicate ammonia release from bacterial breakdown, which signals potential issues. In summary, these field procedures provide immediate feedback and support process control decisions. While they may not be perfectly precise, their real value lies in monitoring trends and making timely adjustments. Consistent methodology and regular checks are key to keeping your system within optimal operating parameters.